Howdy nerds. Alrighty, so this video is being recorded during my planning period because I just found out that I don't have a lesson video for the beginning of section 3.3's complex numbers. So there won't be any questions from the class because I am alone in here, but you know, it is what it is. I wanted to make sure that I had complete videos. So our lesson is called complex numbers, but before we can even have an idea of what a complex number is, we need to first talk about what it means for something to be a perfect square and therefore how to take its square root. A perfect square is something that you get anytime you multiply an object to itself. So when you're talking about numbers, you're talking about 1 squared means 1 times 1, 2 squared 2 times 2, 3 squared 3 times 3, so on and so forth. So right down here, we have to figure out what all of these things are squared because you want to know, at minimum, your first 10 perfect squares. You would really like to know the first 15 perfect squares, and if you know more than that, well, kudos to you. 4 squared is 16, 5 squared is 25, 6 squared is 36, then we go to 49, 64, 81, and 100. Like I said, you definitely have to know those. Past that though, 11 squared, 1, 2, 1, 12 squared, 1, 4, 4, 13 squared, 1, 6, 9, 14 squared, 1, 9, 6, and 15 times 15 is 2, 2, 5. Anything after that is just bonus, okay? So we use these numbers and multiples of them in order to simplify radicals, things that are not perfect squares. Like right here, 18 is not a perfect square. But that doesn't mean that we can't clean it up a little bit because hopefully you notice that 18 is actually 9 times 2. What you're doing is you're trying to figure out which one of these green numbers you can divide the radical by. And we're talking about the number inside the radical. It's called the radicand, ends with a D. But you're trying to figure out what perfect square could I divide 18 by? And I could divide 18 by 9. If there's more than one, you want to go for the biggest one. But and everything's divisible by 1, so 1 never counts. So what we have here is 4 times, and we're going to break the 18 up into a perfect square and whatever's left over afterwards. I like to identify the stuck object. There's nothing I could do with this too. It will be inside the square root no matter what I do. Notice I put this little multiplication dot here between the 4 and the square root of 18. That's to remind you that anytime you press a number against an object in mathematics, that means times. But also, because I'm about to liberate this 9, I could take the square root of 9, and the square root of 9 will get to come out of the radical. But there's a multiplication dot there. The square root of 9 is 3. And there's nothing I could do with the 2. It is stuck inside, and 4 times 3 is 12. So that is how you reduce 4 times the square root of 18. Now here we have a 4 root 18 again, so we don't need to simplify this again. But it says 4 root 18 minus 3 root 2. These are not like terms. Things with radicals are only like terms if the radicals match perfectly. Treat them like 4x and 3y. You know, they don't match. They're not like terms. I can't combine them yet. So 4 root 18 we know cleans up to be 12 root 2. So this is actually 12 root 2 minus 3 root 2. And if we're treating the root 2's like objects, this could say 12 cookies minus 3 cookies, which results in 9 cookies. So there you have it. Once they are like terms, you can add and subtract all day long. Now this example, it says 2 root 50, but just to make sure that we get a more diverse set of questions, I would like to change this to 2 root 75. And over here, we'll change it to 2 root 75 plus root 12. Just to make sure I have enough different kinds of examples. So you're looking at the number 75, and once again, that's not a perfect square. So you look up here and you ask yourself, which of these numbers can I divide 75 by? That one. 75 happens to be 25 times 3. Again, this is not a required step, but I like to identify what is stuck inside the radical. That 3 will forever be trapped in there. It can't come out. But I can take the square root of 5 out. Square root of 5 is, oh crap, I already said the answer. Square root of 25, and the square root of 25 is 5. I hate when that happens. 2 times 5 is 10. So we have 10 root 3. And just like I did in purple, right here, I've got that 2 root 75 again. I don't need to go through all this work again. I already know that this is going to be 10 root 3. But this one, well, 12 is divisible by one of my perfect squares, that one. 12 is 4 times 3. This 3 will be trapped in here, but the square root of 4 will get to come out. So I have 10 root 3 plus, the square root of 4 is 2. 2 root 3. Now these are like objects. 10 root 3s plus 2 root 3s gets me 12 root 3s. Yeah, buddy. Now for this last example, I have the square root of 244. Look, that's a big number, right? 244. And let's just say, worst case scenario, you can't instantly see a perfect square that you could divide by. You could always just break the number down into its smallest possible components. We call this prime factorization, or maybe you've heard it called a factor tree, anything like that. So we're going to look at the number 244. We're going to ask ourselves, what is the smallest number that I know I can divide this by? Other than 1, 1 never counts. Well, the smallest number I see that I can divide this by is 2, because all 3 of these numbers are even. So let's divide it by 2. 2 divided by 2 is 1. 4 divided by 2 is 2. 4 divided by 4 divided by 2, is 2 again. Keep that up. This number is even. I can divide it by 2 again. 2 goes into 12 6 times. 2 goes into 1 1 time. And nothing goes into 61 except for 1 and 61. So these 3 numbers are the prime factorization of the number 244. That means I could have written it like this. You see, but what square roots do is they ask what number times itself would get me the number I'm looking at on the inside of my radical. Well, here's that 2 times 2, right? That would get me a 4 on the inside. And that is a perfect square. So essentially, anytime you see a pair of numbers like this that are exactly the same, they'll get to come out. So 2 times 2 is 4, but what the square root of 4 is 2 on the outside, where the 61 is trapped on the inside because it's prime. So these two objects, because they match, the square root bar turns them into a single object and springs it as a single object. So the 2 got to come out. So if the number's big, or you can't instantly see the largest perfect square, because sometimes, let's say you don't know the multiples of 16, but you do recognize that 4 could go into a number more than once, well then just take 4 a couple times. It's not a big deal if you have to split them up. It's not a problem. And square roots of stuff on the inside, when they come out, you just multiply them on the outside if you need to. Here's the square root of 244. Once again, we know that that is the number 2 root 61. And 5, ladies and gentlemen, is a prime number, so there's nothing I can do with it. I'm finished. That is as good as it gets. So, what is the whole purpose of all this review of reducing radicals? The purpose of it is to talk about what happens when we try to take the square root of a negative number. You see, one of the things that we talked about earlier in the year was that you cannot take the square root of a negative number. I mean, I grabbed my scientific calculator, I tried to take the square root of -1, and his calculator says, bork, domain error. That means, no, it can't do it. Well, it doesn't mean it's impossible. It just means that this calculator can't do it. And the reason why this calculator can't do it is because this calculator can only do things in the real number system. But there's a whole nother number system out there called the imaginary number system. That doesn't mean that it's made up. It doesn't mean it was created. It just is the name that people gave it. So because perfect squares are always positive, I mean, look up here. Those are all positive numbers. Because perfect squares are always positive, there is no way to find the square root of a negative number using the standard number system that you know and love to this point. Therefore, the square root of -1 is called I. That is its numeric value. The square root of -1 equals this fancy I. Let's be really clear here. I is not a negative number. It is the square root of a negative number. Okay? This is positive 1I. And yes, there are negative i's as well, like -1i, -2i, -3i. But you could treat them almost like variables or objects. It is unfortunate that they're called imaginary because that does make people think that we just kind of made them up. And by we, I mean the mathematicians. That's right. I am considering myself one of them. They were discovered, and we just needed a symbol to represent this value because this value is tough on our pea brains to understand, so we give it a symbol. It's like pi. You know, nobody knows what pi equals. I mean, we can approximate pi, but it never stops. It has no pattern. So the best thing that we can do with our language and our number system is give it a symbol. Same thing is going on with the square root of -1. Square root of -1 just isn't possible to describe it using our real numbers because it exists outside of our real numbers. So we give it a symbol. They're not made up. They are extremely useful. You can't even talk about the study of electricity without talking about complex numbers and imaginary numbers. They are just a necessity of a lot of things that we do. So let's reduce more radicals, simplify more radicals, only this time there are negative numbers inside of them. We are going to say that the square root of -1 is always an I, and you can never leave a negative symbol underneath a square root bar. That means we need to split it apart. And if we are considering -1 to be a perfect square, then I'll just go ahead and say that -28 is -1 times 28. But what perfect square can you divide 28 by? You're looking up at these green numbers, and it's that one, 4. You can divide 28 by 4, and it goes in 7 times. You see, the only thing that is stuck here is this 7. It's the only thing that's trapped. So you could take the square root of -1 out. It's liberated. Square root of -1 is I. The square root of 4 is 2. And 7 is trapped. And this is not a wrong answer to say I2 root 7. But it just feels weird because in mathematics we put our objects after our numbers. So you can either say this is 2i root 7 or 2 root 7i. They're both correct. I mean, there's some people that'll be picky about the order of this. It just feels more natural to say 2i root 7. So that's how I'm going to write it. And that's it. But you know, if we're comfortable saying that the square root of -1 is I, then there is no real reason to actually split these two numbers up. This could have just been thought of as saying the square root of -4 times 7. And then what we could have said was, if the square root of 4 is 2 and the square root of -1 is I, let's just say the square root of -4 is 2i. Square root of -9 is 3i. Square root of -16 is 4i. Square root of -49 is 7i. So on and so forth. In fact, I say we add it to our table up here. -1 is now a perfect square. The square root of -1 is I. There, it's on the table now. It is official. It's canon. There it is. We talked about the square root of 75 up above. It was the one that I hand wrote in. Well, how about we say, instead of saying -75, why don't we say it is -25 times 3. Identify the 3 as the stuck object. We've got this -3 times the square root of 25 would have been 5, so the square root of -25 is 5i. Boink. And we still have this root 3, so -3 times 5i is -15i. At this point, someone tries to ask a question, but wait, wouldn't this give me a positive number since I is negative? No. I is not a negative number. I is the square root of a negative number. That does not inherently give it symbol, okay? So I is not a negative number. -3 times 5i is -15i. All right. Last one on the front here. 2 root -48. It would be great if you knew what perfect square you could divide 48 by. Now, a lot of people won't instantly see it, and that's fine. Why don't we do this one the slower way? How about that? What is a small perfect square that we can see, that we can divide 48 by? I'm hoping that you just thought 4. So let's actually say -4. And let's go ahead and split that up. Let's factor tree it, okay? 4 goes into 48 12 times. And 12 is also 4 times 3. So we could have done it like that. It's a slower process, but maybe you didn't instantly see that you can divide 48 by 16, because that's what 4 times 4 is. Regardless, it doesn't matter. If you have to do it this way, that's fine. Just get them right and understand what you're doing. I've got the 2 on the outside. Oh, I almost forgot the circle the stuck thing. Purple feels good. 3, you are trapped. Okay. Square root of -4 will be 2i. Square root of 4 will be 2. And, well, that 3 is trapped. Can't do anything with it, so 3. 2 times 2 times 2 is 8. So this is 8i root 3. Ta-da! That's it. Almost finished with part A of the notes. We'll get through this box up here and talk about what some of the implications of this box are, and we'll be done with it. By definition, I to the first power is the square root of -1, which is just I. Okay, so this table right here is all about powers of I. You see, if imaginary numbers are themselves numbers, then we must be able to do everything with them that we could do with standard numbers. We should be able to add, subtract, multiply, divide, powers, and roots, so on and so forth. Here is the powers. I squared. I squared means something times itself, right? And that means, this means I times I. But I is the square root of -1. So I could have said square root of -1 quantity squared. But when you do that, you are squaring a square root, and squares and square roots cancel each other, leaving you with -1. So I to the second power, I squared, is a real number. It's -1. That's neat. I to the third, well, why don't we just say that that's actually I squared times I. And the reason why I'd want to do that is because I squared is -1. So I cubed is -1 times I, which is just -I. Remember, I is not a negative number. It's the square root of a negative number. And then this last one in here says I to the fourth. Think of I to the fourth as saying I squared times I squared. Again, the reason why I want to do it that way is because I squared is -1. This now says -1 times -1, which is 1. Another real number. And because of this result, since I to the fourth is 1, so is I to the 8th, I to the 12th, I to the 16th, I to the 32, I to the 100. In general, there are only 4 values that powers of I can take on. So I to any power you can think of will be one of these 4 values. It'll either be I, -1, -I, or 1. And it literally goes like this. I to the 1, 2, 3, 4. I to the 5, 6, 7, 8. I to the 9, 10, 11, 12. So on and so forth. And this gives us the ability to simplify big things, big powers of I. For example, I could say I to the, let's see, I'm just going to make up a 3-digit number. How about that? How about 2, 3, 1? I to the 231. We're going to figure out what this equals together. Now, it would be helpful if you knew the multiples of 4 trick. I can tell you right now, this is not a multiple of 4. The trick for multiples of 4 is just look at the last 2 digits in any number. If it ends in a 2-digit number that is divisible by 4, the whole thing is divisible by 4. So what you're looking for is a number that's smaller than 31 that you could have been able to divide by 4. The number smaller than 31 that you would have been able to divide by 4 would have been 28. That means I to the 231 can be thought of as saying I to the 228 times, because remember when you multiply numbers with the same base, you add their exponents, I to the, the remainder would have been 3. See, if I had divided this by 4, the remainder would have been 3. This is just a whole bunch of these. It's a lot of them. Looks like 57 of them. This number right here, 228 is 57 times 4. So I to the 228 is literally 57 I to the fourths, all multiplied to each other. But since I to the 4 is always a 1, this is literally 1 times itself 57 times. But that just means this whole thing right here just equals 1. Who cares how many times it happened? And I to the third, well, that's just negative I. So I to the 231 is actually negative I. So there it is. The general rule is, if you were going to divide the exponent by 4, what would the remainder have been? Because the remainder is the only power you care about. All the ones that were divisible by 4, that's just a whole bunch of 1s doing nothing. And that, nerds, was the entire 3.3a lesson, just without my students asking questions during the video. If you have questions, please feel free to shoot me a message or ask me in class. I'll see you soon.